Hi, everyone. So I'm going to briefly talk about the Reynolds transport theorem and its usefulness in deriving the equation for the conservation of mass. The first thing we're going to do is start with some definitions. So the first thing we have to refresh our memory about, because it is discussed a bit in the book, is the concept of Eulerian versus Lagrangian perspective. So first of all, the Lagrangian approach is talking about more or less particle tracking. So you have uh, particles moving in a system. So in this case, it's particle A particle moving from A to B along this path line. That is the Lagrangian approach. The Eulerian approach is what I call kind of like the lazy man's approach, where you're just tracking the ins and outs, right? Through a control surface. So this is not just one particle or one a system. This is more of a systemic perspective. It's talking about if you were to be stationary, okay, how much is passing through that particular location, and of course how much is leaving. Okay, so that's more of the Eulerian perspective. We also need to make sure we are clear on the definition of discharge, or also known as a volumetric flow rate. The definition is it is the volume of fluid that passes through an area per unit time. Your book sometimes, actually, your book uses the notation V dot, which is the rate of change of velocity, of volume with respect to time. We're not going to use that in my class just because I'm a hydrologist. We always use Q. That's what we use. B dot is fine, but we're going to use Q. So going back to the definition, Q is the volume of fluid that passes through an area per unit time. An alternative equation is going to be more commonly used is velocity multiplied by area. So both of these are how we would define our volumetric flow rate. The common units for flow rate, and I want to make sure that you listen and write this down. The most common is CFS, where C means cubic, F means feet, and S means second. So cubic feet per second is feet cubed per second. In your book, and a lot of the literature, it just says CFS, and you might not understand where that comes from. It's just cubic feet per second. Another common unit is feet cubed per minute, gallons per minute. Okay. Make sure you have these written down. And the SI unit, it's meter cubed per second. We also sometimes use liters per second. And this is a common one when you especially when you get to water resources. This is acre foot per hour. That's a very, very common unit for volumetric flow rate. So make sure you have these written down somewhere. Okay. Now this is kind of showing a cross-sectional view of how a flow rate is calculated. So you have your center line, right, in the middle of your pipe. And at that center line is where we have our maximum velocity, okay? And all we're doing is we're calculating the velocity that passes through this cross-sectional area. So if you took a slice of the pipe, you have the area, right, where the area is just pi r squared, or pi over 4 diameter squared. You just calculate that cross-sectional area and you multiply it by the velocity at the center line, okay? So in a pipe, the velocity increases from 0 at the wall to a max at the center. I want to just quickly explain what that means. You have one pipe that has 2 walls, okay? We're going to draw our velocity profile. Now, at the wall of the pipe is where we experience our maximum amount of friction. So the amount of friction that's opposing our movement. So that's where our velocity is approximately 0, okay? As we reach the center line, that is where our velocity is maximized. Velocity is maximized, and our velocity is like a parabolic shape. So at the center line, we have our maximum velocity, and at both edges, our velocity is equal to 0, okay? So the question is, what is the volumetric flow rate through any differential area, okay? So Q is going to be the differential V velocity multiplied by dA, okay? You essentially are going to take that integral with respect to that cross-sectional area, okay? So I'm going to show you a few other useful equations. This first equation is our mass flow rate, which is denoted as m dot. Again, we would take that integral across that cross-sectional area, and we would multiply our Q calculation, I guess this would be dq, by our density. So if we don't have if we have a predictable area similar to like a pipe, then our m dot is just going to be density multiplied by velocity multiplied by A, or densities multiplied by Q. That's going to be our mass flow rate. Okay, combining discharge and mass flow rates, you can calculate flow rate either using our velocity multiplied by area, or it would be our mass flow rate divided by our density. So these would be alternative and perfectly acceptable ways to calculate our Q, given that we have a predictable area, and we would have to use this approach if we actually do have our area changing, okay? Those would be our useful forms. And again, we have our m dot, we have here is density multiplied by our, again, velocity multiplied by area, and you can also get it by calculating your density by Q, okay? So those equations, write them down, make sure you have them handy. They are incredibly useful, and they will be an important part of our conservation of mass equations. So we have both of our equations here kind of showing the differential forms. So the differential form allows you to calculate the change in the mass flow rate as the area changes. The area of the pipe is not always constant. A lot of the times we'll be looking at the a cut of the pipe, and it is constant. So we have to start out with this general form, and what we're going to then do now is define what's called our control volume, okay? So the control volume approach requires an understanding of a system and the control volume, where a system is a continuous massive fluid that always contains the same fluid particles. So I'm just going to kind of go to this picture here. So this is, imagine this is like a ball, a sealed ball moving through the fluid, okay? That is considered the system perspective, okay? A control volume is the volume of space enclosed by a control surface that may actually deform in time. It also may have mass move in and out, okay? So that would be our control volume. So again, moving forward, this would be more appropriately like, again, like a 3D surface. You have some volume of space that's defined by the surface. Now, in this systemic perspective, it's kind of closed off, okay? You're tracking the particles that are already in the system. The control volume is different because you could have things freely entering, you can have things freely being stored, and you can also have things exiting. So it is very different, okay? The control volume, an example of a control volume that is not changing, I'm talking about the volume is staying the same, is when you have something like a pipe. So here's our pipe, Here is our control surface entering, and here is our control surface exiting, okay? And here is our outline of our control volume, and here is, again, our outline. Okay, we have particles moving in and out of our control volume, and we're essentially going to start tracking that movement, okay? One last thing to define or bring up is this intensive versus extensive properties. So intensive properties are independent of mass, and our extensive properties do depend on mass. Okay. Intensive versus extensive properties. So extensive properties, again, are a function of mass. So you have mass, momentum, energy, weight, things like that. When you're trying to define the intensive properties, you essentially divide by mass. So in this case, if you divided by mass, you'd get 1. If you divided by mass, you'd get velocity. If you divided by mass, you'd get energy per unit mass. And in weight, you divide it by mass, you'd get gravity. So those are examples of extensive and intensive properties. In the Reynold transport theorem, which I'm going to introduce next, the capital B is the extensive property, and lowercase b is the intensive counterpart, okay? So Reynold transport theorem, which is RTT for short, is a fundamental theorem to the control volume approach. It relates both the Eulerian and Lagrangian approaches and is derived by considering the rate of change of an extensive property as it passes through a control volume. This is our equation for the Reynolds transport theorem. Capital B and lower b can be just about anything. It just allows us to translate from a moving system to a stationary control volume. It, again, looks really complicated, but I'm going to walk you through the derivation to show you it's actually quite simple. And actually, I like this perspective because it shows you on the left-hand side we have Lagrangian, on the right-hand side we have Eulerian. So on the left-hand side of the equal sign, this means the rate of change of property B, again, which is an extensive property of a system. This means the rate of change of property B in a control volume. So you can see it's relative to the control volume. And this is talking about the net outflow of property B through a control surface. What I want you to do is I want you to note that we're talking about what goes out of the system minus what went into the system. So make sure that you label that integral out in, okay? It's gonna be really, really important. So what we're gonna do now is we're gonna use the Reynold transport theorem to derive the conservation of mass. So just writing this really quickly. Lowercase b rho d volume plus out minus in of b rho directional velocity dA, okay? Let me just, there we go. That's a directional velocity, so you don't need the unit vector there. Kind of overkill. Okay, so what we're going to do is we're going to derive the conservation of mass. And the extensive property is going to be m for mass, and the intensive property is just the extensive property divided by mass, which is just 1. So I'm going to make the substitutions into the Reynold transport theorem. So we have dm of the system, dt is d dt integral control volume 1 multiplied by density d volume is integral out minus in 1 density directional velocity dA. Okay, this equation is just substituting our extensive and intensive properties into our Reynolds transport theorem. Now, I want you to focus on this left-hand side of the equation. This left-hand side of the equation essentially violates some basic rules. You can't have mass created or destroyed just spontaneously. So we essentially take out this left-hand side of the equation and mark it as 0. Okay, so I'm just going to do that really quickly. We can keep that red, just so you know. This is our starting point for our conservation of mass. What I'm going to do is I'm going to make some assumptions now. So we're going to assume that area is not changing, okay, across that cross-sectional area. So this essentially just becomes our total area, okay? So we have 0 is d dt, control volume, rho dv, plus our summation out of rho va minus our summation in of rho va. That's our first assumption, okay? Now what we're going to do is assume that our control volume is not changing with respect to time. An example of this would be if we had a rigid pipe, okay? If we have a rigid pipe, then this integration here is 0, right? It's not changing with respect to time. So we can essentially eradicate it from our equation. So we end up with 0 is the summation out rho VA minus summation rho VA in, which is going to be summation rho VA out equals summation rho VA in. Okay, so that is going to be after our second assumption. Okay, now we can write this a few different ways. We can keep it the way it is. We can also say that sum of rho Q out, right, because VA is equal to Q. So we can say summation of rho Q out is the summation of rho Q in. We can also say, what is this equal to, right? This is going to be summation of M dot out is summation of M dot in. Okay, so this can lead into one more assumption. So we can assume that the densities out is equal to the densities in. This must be understood in some way from the problem statement. If you have a combination of two completely different type of fluids, you can't make this assumption. But if you have water in, water out, you can. So this actually ends up turning into the sum of Q out is the sum of Q in. So these two equations, here and here, if you have the same densities, this just cancels, okay? Okay, but you have to leave them in if they're different. An example of this would be if you have, let's say, a Y-shaped tube or system here, okay? You have, in one pipe, you have fresh water, and in this pipe, you're mixing it with sludge, okay? That means as these fluids meet, okay, this has some density, and this has a different density, okay? As they meet, they're going to combine and create a completely different mixture, which has its own mixed density, okay? It's not going to be conserved. It will absolutely change. So in this particular scenario, you would use, so let's say this is 1, this is 2, and this is 3. then you would have rho 1 Q1 plus rho 2 Q2 is equal to rho 3 Q3, right? Does that make sense? These two together have combined to create this mixture, okay? So these are your ins and these are your outs. This is your out, okay? Now, one thing you must absolutely understand is that, yes, you have a combination of densities and flow rate in this equation. What you also have is you must conserve your flow rates in the entire system, okay? Flow rate just doesn't disappear. It must be conserved, okay? So the flow rate entering all of that flow rate is the flow rate exiting. So you also have Q1 plus Q2 is equal to Q3. You have both of these equations in this problem, okay? You can use both of these equations to solve for some unknown, okay? Again, if you just have, like, let's say we look at this pipe and you just have fresh water in 1, 2, and fresh water out at 3, okay? If we look back at this equation here, then these go away. And then you just have this, okay? So if you have the same fluid, one fluid, then you just have Q out is Q in. If you have your densities are constant. But if you have changing densities, then you have both. Okay, I just want to make that very clear. I hope this was helpful. Let me know if you have questions about the conservation of mass.